Good, thank you. So I'm just going to give you a warning, first of all, and that is that you may find this lecture confusing, and I should be surprised if you don't, because I find it confusing myself. And secondly, an apology. It's an update of a lecture I gave in Zurich just before the pandemic. It's a shock to realize that now. It's early in 2020. I had expected to have many more different things to say, but I was wrong. So some of you may have heard much of this before. There are some new things, but not everything is new. So this is an outline. What do we want from replication? I'm going to discuss p-values as the inferential villains, more or less. One thing you can get all practicing statisticians to agree on these days is how awful p-values are. On the other hand, statisticians tend to quite like confidence intervals, and there is a duality between p-values and confidence intervals, so it's a bit baffling as to how one can be okay and the other not, and I shall have a look at this. Will Bayes factors prove superior? And then give you some conclusions. What do we want from replication? So a current view is that we have a replication crisis. But to agree whether this is true or not depends at least on agreeing what constitutes replication. For example, a lot of the discussion has been about not replicating positive claims. People seem to worry a lot about false positives. But there doesn't seem to be any discussion about false negatives. And if we're only worried about false positive, the solution is very, very simple. Just request p equals 0.000000001 as proof of an effect, and the problem is solved. We're not going to have any false positives at all. Of course, we'll have masses of false negatives. What do we want from the analysis experiment? Do we want a statement of the evidence from that experiment, a statement about the state of nature, or a prediction about a future experiment? These are different things. And my argument is that if there are problems, they have a lot less to do with the choice of inferential system or statistic, and a lot more to do with appropriate calculation. So some of what I'm going to be talking about has been discussed at great length in philosophy in general under the heading of theories of truth. And this is taken from a paper by Ralph C. Walker, in which he considers possible theories of truth. I'm only going to have a look at two: the correspondence and the coherence theory of truth. The correspondence theory of truth is essentially about external consistency. The correspondence theory of truth holds that for a judgment to be true, it's for it to be correspond to the facts, and it's particularly associated with the work of tasking. Coherence is much more like a particular Bayesian requirement, internal consistency. The coherence theory of truth equates the truth of a judgment with its coherence with other beliefs. And quite a lot of elegant development of Bayesian theory is based upon the idea that you should not place yourself in a position of being certainly able to lose a bet, the Dutch book argument, essentially a coherence argument of beliefs. Now, an interesting case study to have a look at, a very impressive one, is the Many Labs project. And I'm rather nervous because I know there are a number of psychologists on this call, and they're much more familiar with this than I am. And this particular experiment tried to replicate lots of different key experiments in psychology using different laboratories at different locations and reported the results. A very impressive collaborative organization, in my opinion. I also have a confession to make, is that many people found it rather disgraceful that some of the particular claims in psychology were not replicated. I had a disgracefully poor opinion of psychology as a discipline. I thought it was absolutely extraordinary that so many things stood up. And if you have a look at this particular diagram here, which gives you on the left-hand side, it tells you what the various particular claims were that were being attempted to replicate. You will see that they held up rather well. The X's are the original results. The zeros are the replications in the various different laboratories, US and international. And then we've also got some 99% error bars with the large green circles representing the point estimates. You can see, in fact, that some of the anchoring studies, the original studies, were really over-replicated in the sense that the evidence subsequently was much, much more impressive. But two priming studies in particular, flag priming and currency priming, were not replicated. And I don't personally find this particularly shocking. I think that this is the sort of thing that will occur in particular fields. And I'm slightly puzzled as to why this caused such a particular fuss, but this is behind a lot of the discussion on replication crisis that has been going on. So recommended reading here regarding replication is this particular paper by DeVesa et al. And what the authors point out is that reproducibility is essentially a parameter of the population of studies. If you're going to look at a particular studies of replicating, as the Many Labs project did, then the reproducibility is essentially a property of the population you're looking at. But they also point out that true results cannot be reproduced at will. And it also point out that false results may be highly reproducible. This is something we can agree on. There may be some hidden flaw in the way in which everybody are doing experiments, which is not to do with the inferential setup, which is to do with what they're actually failing to do correctly in the experiments. They also make the rather controversial claim that pre-registration is not necessarily valid inferences. I've gone back to this paper a number of times and decided there are many more things in it I need to read, but they have attempted to set the whole field of replication on some sort of a firm footing, or at least a footing that can be debated. And I would recommend those of you that are interested in replication per se, have a look at this particular paper. So p-values as inferential villains. So more and more statisticians and others are claiming that the p-value is the villain of the story, and that usually the person that introduced this reprehensible way of looking at data to the world was R.A. Fisher. But this is actually incorrect historically. Fisher was not the first to use it. You can certainly find p-values in Pearson's work. That's Carl Pearson, not Egon Pearson. And his major innovation, in fact, was to double them, making them perhaps more conservative, at least if you naively regard low p-values as being evidence, then the fact that they're not as likely to be low because you're doubling them is a conservative move. And p-values are fairly similar to one standard Bayesian approach to inference. And this particular approach is using uninformative prior distributions and then looking essentially at the dividing problem. You're trying to guard against the problem, for example, of choosing the worst drug in an experiment. You want to guard against the error that the treatment that you will recommend is actually the worst of two treatments, and you've not got any particular belief that the two treatments will be identical. And if you have a look at the paper by Benjamin, Berger and Johansson and so forth, Redefine Statistical Significance in Nature, an article which sends shockwaves through the world of laboratory studies and other areas, then you'll see that they said the following: for fields where the threshold for defining statistical significance for new discoveries is p less than 0.05, we propose a change to p less than 0.005. This simple step would immediately improve the reproducibility of scientific research in many fields. But they didn't really present an analysis of this. It would reproduce in one particular way it would improve the reproducibility of positive results, but it's not clear that it would reproduce the negative results. And in any case, for this to be true, it depends upon a particular sleight of hand. The significance level reform can be presented in terms of this particular plot. I have a Z value that one might calculate from an experiment on the x-axis. And on the y-axis, I've reported the p-value or the likelihood ratio. Here, what I'm actually doing is I'm simply taking the observed statistic as being one particular value that determines the likelihood ratio, and the value of 0 as being the likelihood that forms the ratio, and the value of 0 as being the other. And what you can see highlighted is a value of 0.258 corresponding to, for the likelihood ratio, corresponding to the much smaller p-value of 0.05. And this, I think, is part of the criticism, is that basically the p-value may seem small to you, but the likelihood ratio is not nearly as small as that. And therefore, what it would be nice to do would be push this p-value smaller until the two seem to agree. And their particular recommendation of going for 0.005 would correspond to a Z statistic of 2.567. And the corresponding likelihood ratio would be 0.036 rather than 0.258. But everyone knows you can judge significance by looking at p-values, and nearly everyone knows that you can also judge significance by looking at confidence intervals. For example, does the confidence interval include the hypothesized value? Rather fewer people know that you can judge p-values by looking at confidence intervals, but you can just calculate lots of different degrees of confidence, a so-called confidence distribution, and see which one just excludes the hypothesis value. It seems plausible, therefore, implausible rather, if p-values are inherently unreliable, that confidence intervals must be reliable. So I'm going to have a look at a confidence interval and see how this works. Here is a confidence plot. This is a trial in asthma with a disappointing result, which will be described as being very nearly a trend towards significance. It is for this sort of creative statement that we statisticians that have worked in drug development rely on our physician colleagues in writing up the results for a particular trial. And you can see that the estimate here was just a little bit in excess of minus 40, so about minus 38 or something like that. What I've got here, the blue curve is, in fact, all the possible confidence intervals that I might calculate, with confidence being indexed by the y-axis. And unfortunately, the point at which that curve crosses 0 does not correspond to 95% confidence or even something rather greater, but only to 89.61% confidence. And in fact, the corresponding p-value is 0.014. So the confidence is simply mirroring here what the p-value shows us. So the confidence interval paradox, how can we explain this? What I've done here is I've simulated a number of confidence intervals from a particular situation that I might assume applies in asthma, where in fact the treatment effect, let's say, of a beta agonist compared to a placebo is 300 milliliters of forced expiratory volume in 1 second. I remember this universe, so I know what the truth is. And I've simulated a series of confidence intervals, 95% confidence intervals, and I've marked the ones that are that don't include the true effect of 300 in red. The rest, the black ones, the black diamonds, include the true effect. And here I have to make a confession in view of the fact that Mendel has just been accused of having fabricated his data. Of course, what I did here was I fiddled around with the simulation seed until I got exactly 10 confidence intervals that didn't include the 300. So if you think that getting exactly 5% of them that don't include the true value is too good to be true, well, the answer is yes, it is. I cheated. But, well, what does this mean, in fact? They do not include the true value. Is there any way I could recognize this? Well, there is, in fact, because I also have got baseline differences between the two groups, which are also simulated from a bivariate normal distribution, etc. And if I plot the confidence intervals against the baseline difference, I now have a means of recognizing areas in which the confidence intervals are less likely to include the true treatment effect. And basically the situation is, if the baseline difference is impressive negatively already, or if the baseline difference is impressive positively already, then in that case, I can recognize that the probability that the confidence intervals will not include the true values is rather greater than 5%. So I've been given myself here with this additional information and means of recognizing questionable confidence intervals. What can I do? Well, of course, I can use an analysis of covariance here. So what I can do is I can cash in on the information, I can use it, I can absorb it in my analysis. And what I now have is I have a miraculous situation in which, again, I have 10 particular confidence intervals, which no longer include the true value because I've adjusted for the baseline difference. You can imagine how long it took me fiddling around with randomization seeds in order to get both of these diagrams to produce exactly 10 intervals, which did not include the true value. I hope you're impressed. So here we have the result. Now the situation is that I don't really have a means of recognizing things. The confidence intervals that were previously at risk have been shaded in red, but in actual fact, I don't know. I don't know anymore that they are. It seems to be, everything seems to be okay. By the way, there's a benefit as well. What I get by doing this is I get much narrower confidence intervals. That's basically, I've consumed the information in the baseline by doing this. Is there any way other ways to do this? Well, of course, I can take my simulation and I can sort all the confidence intervals by their value. So here I'm actually sorting them by their value. And now what I find is that the ones for which the estimate were particularly high, or the ones for which the estimate was particularly low, don't include the true effect of 300 milliliters. So that's fairly obvious, if you like, fairly impressive. You may say, well, why can't we do this in practice? Well, of course, in practice, the problem is I've only got one confidence interval. Here I've simulated 200 for myself. I've only got one of them. How do I know that it's unusual? What method do I have of telling me that they're unusual? Well, the answer is I can recognize that they're unusual using prior information. My prior knowledge in some particular way, my prior knowledge as a Bayesian, can tell me that this confidence interval is improbably large, for example, in which case I can judge that it's more likely to exclude the true effect. So this explains the paradox. Bayesian can still maintain or agree that these three things are true. P-values overstate the evidence against the null. But p-values are, yes, dual to confidence intervals. But 95% of 95% confidence interval will include the true value. But the reason is that those 95% confidence intervals that include 0 have a probability greater than 95% of including the true value. Those that exclude 0 have a less than 95% chance of including the true value. And averaging over the probability of these, everything is okay. So the individual cases are misleading and can be recognized as such. The consequence is that your prior belief in 0 as a special, much more probable value gives you the new means of recognizing the less reliable intervals. Will Bayes factors proven superior? Well, first of all, let's remind ourselves of what it means to be Bayesian. I think there are at least three major approaches. I know that Jack Good famously identified several thousand of them, but I obviously don't have time to go into all of those, and I wouldn't be competent to explain them. But let's say that a formal one, which is automatic, software is readily available. There's no guarantees of anything. They're unlikely to reflect what you feel. They're unlikely to reflect what you know. It's unlikely to predict what will happen, but they may fulfill some sort of formal role. Subjective, which I think in many ways is the most impressive, to come back to our coherence theory, you'll never lose a bet with yourself, they're logically elegant. The main disadvantage is you can't change your mind, you can only update it. Your prior cannot change. Knowledge-based may have some chance of working as an objectively testable prediction machine, useful for practical decision-making. The main problem is it's hard, and it's very hard, and in fact it's extremely hard. But to the extent that I have tried to be Bayesian in my work doing on drug development, then in that case I have tried to identify plausible prior distributions based on reasonable information in order to somehow make the whole thing work. This is a proposal from Held and Ott. Here they are proposing a particular type of Bayes factor, not the one that requires integration over the respective hypotheses that Richard was explaining, but one which essentially is a minimum Bayes factor. What you do is you calculate the Bayes factor as a function of the standardized difference. So let's say the said statistic here, it's called mu. Basically you're just comparing the particular alternative hypothesis, which is best supported by the statistic, with the null hypothesis of 0. And the diamonds here represent the lowest value that this will reach, and it's actually the value that corresponds to the point estimate. And so you could use these particular values if you wanted to as an alternative sort of Bayes factor, minimum Bayes factor. Steve Goodman has made the criticism that p-values have an inferential problem. Maybe I'm misrepresenting him here, but I think he has at least said that there's a way of understanding how they behave. And that is that the probability of repeating a result that is just significant at the 5% level is in fact 50% under either of these two cases. The true difference is the observed difference, or there was an uninformative prior for the true treatment effect, and therefore the p-values are unreliable as inferential aids. But this property, in fact, is shared by Bayesian statements, and it follows from the martingale property of Bayesian forecasts. So if it is an undesirable property of p-values, it's an undesirable property of Bayesian methods also, or it's desirable as a point in favor of frequentist methods. So I'm going to have a look now at a particular simulation in which I'm looking at p-value for trial 1 and p-value for trial 2, and I'm trying to consider how often it is that we actually get significant results. I'm also generating under a mixture of hypotheses. 50% of the time H0 is true, and 50% of the time H1 is true, and I'm using a very, very simple situation where in actual fact H1 is centered on 2.8, but the variance of the true effect around this is 1. And the standard error of the statistic is also 1. So the variance of the statistic is also 1. This is the simulation here. You can see that on the whole, I seem to be getting things right, but there are some blue things which are in the significant area, and there are some red things which are in the non-significant area. As before, but magnified to concentrate more easily on the significance boundary of 0.05. So you can now see that there's quite a crossing over into the area. If I do the same thing for Bayes factors, then I'm going to get a fairly similar sort of situation here. It partly depends on the calibration where I decide to put the boundaries or whatever. This is a particular similar situation with Bayes factors. And in fact, my interest in this stems partly from the fact that within drug development, you're required to have 2 significant results at phase 3. This particular diagram shows essentially the plot in the Z scale, Z1 for trial 1 and Z1 for trial 2. And the 2 trial rule essentially requires you to be, I'm not sure how I can point here, but it requires you to be in this little upper quadrant here, because that's the area in which you will exceed 1.96 for both of the trials. If you pull the true trials, you'd actually get a result with greater power, and that's the blue diagonal line that we have here. So this idea of replication is built into drug development, and we generally don't claim that a result is proven unless we have 2 significant results at the 2.5% level, one-sided, in favor of the particular treatment that you're testing. So here's my comparison of 2 trial strategies. Simulation values are as previously, but the second trial is only run if the first is positive. If the first is negative, there's no point running the second one if we're doing it sequentially, because we're not going to get registration anyway. So how many trials do we run altogether if we use the frequentist rule of p less than 0.05? Well, the answer is 1,372. We did rather better with the Bayesian rule. We only had to run 1,299. There were no false positives in the sense of both trials being significant when the null hypothesis was true. For the frequentist approach, there was 1 for the Bayesian approach. The number of false negatives for the frequentist approach was 68, and for the Bayesian was 133. The number of false decisions, therefore, was 68 versus 1344. And if we look at the trials per correct decision, then in that case, it was slightly in favor of the frequentist compared to the Bayesian. Now, you should not place too much weight on this. I'm sure there are different ways in which would sort the Bayes factor and sort things out, which would not favor p-values in this particular way. But I tend to think I'm rather suspicious of ways that point the finger at p-values, or claims that point the finger at p-values, that don't consider false negatives either, and don't consider the way in which p-values are used in practice to support claims in an area which is particularly important and where great care is taken to make sure that it's done correctly, and that is drug development. What does this amount to? Well, nothing more than this. Given the same statistic calculated for 2 exchangeable studies, and in advance, the probability that the first is higher than the second is the same as the probability that the second is higher than the first. That's perhaps not so obvious from the discussion that's gone before, but that's essentially my answer to Goodman. It's hardly surprising, is it, that, you know, if you calculate a statistic that to 2 statistics, that the probability that that the second statistic is greater than the first is the same as the probability that the first is greater than the second, unless something else is known. And once a study is reported, for any bet to be more than a coin toss, other information has to be available. For example, that given prior knowledge, the first is implausibly low. It's an implausibly low p-value. So I would sort of tend to agree with what Richard was telling us. One has to be very careful in using Bayes factors, and one has to be very careful in specifying prior distributions. That's a reminder that I should stop in about 5 minutes. So let's consider the following possible questions that we might have, going back to my initial point about what is it we actually want from replication. In the first experiment, B was better than A, P equals 0.025, so just on the boundary of significance as required in drug development. Question 1. What is the probability that in a future experiment, taking that experiment's results alone, the estimate for B would after all be worse than for A? Question 2. What is the probability, having conducted this experiment and pooled its results with the current one, we would show that the estimate for B was after all worse than that for A? Question 3. What is the probability that having conducted a future experiment and then calculated the Bayesian posterior using a uniform prior and the results of the second experiment alone, the probability that B would be worse than A would be less than or equal to 0.05. And this particular diagram shows the answer to these three particular questions. And question 3 is the probability that A is better, alpha, here. And you can see that it's very much dependent on the size of the experiment to come. The ratio of the first, the x-axis is the ratio of the first standard error to the second. So essentially large values of the x-axis show that the second experiment is much more precise than the first one. And what we're going to get if we've used an uninformative prior distribution and we get a p-value of 0.05, going back to the very old interpretation of tail error probabilities that there was before Fisher came along, then in that case, a p-value of 0.025 would correspond to a probability of 0.975 that in actual fact B was better than A. But we're not going to see that replicated in another experiment unless that experiment is infinitely large. If it's infinitely large, we reach this value of 0.975. If it's not infinitely large, we get values much less than that. And in particular, if it's the same size as the current experiment, the value is only 0.05. But to take this replication probability as being inherently a feature of p-values, or indeed of any system, is absurd. It would mean that our inferences, having conducted an experiment, depend upon the following. We're going to repeat this experiment again. We're going to repeat it exactly once. The experiment we're going to run must be exactly the same size as the experiment we ran in the first place. And our judgment of efficacy depends entirely on this second experiment. And I don't think anybody who stops to think about it could think this is a reasonable way to proceed. So what we're really interested in is following. We're interested in the truth. We're not interested in replication per se, certainly not if the replication study is no larger than the original study. We're interested in what an infinitely large study would show. And this suggests that we're really interested in a meta-analysis as a way of understanding the results. And this is actually rather Bayesian. So Benjamin et al. Revisited, how could it be possible that they can actually claim that you would get increased replication? Well, the answer is they cheated. If you have a look at what they proposed that you would have an initial result significant at p less than 0.05, but you would judge it replicated if you had p less 0.005, sorry, but you judge it replicated if you have p less than 0.05 in the following study. But this is a really strange thing to do. They're actually suggesting that what you should have is you should have a very large study to start off with, and then you should replicate your result using a rather smaller one or a less impressive one. I don't think this particular claim was thoroughly investigated. I'm skeptical as to whether this is a logical way to proceed. By the way, and nothing I've said so far shows that significance is better than base values. Different parameter settings could show the opposite. Different thresholds could show the opposite. It does show that reproducibility, at least in my opinion, is not necessarily the issue. The strategy with poor reproducibility is marginally better, but this doesn't have to be the case, but it shows it can be the case. It raises the issue of calibration, and it also raises the issue as to whether reproducibility is a useful goal in itself and how it should be measured. I'm going to skip George Biddle-Airy, who's an interesting character who had a lot to say about combining evidence in the interest of time. So I'm now going to sum up what I have to say. The connection between p-values and Bayesian inference is very old. The idea of carrying out frequentist star fixed effect meta-analysis but giving it a Bayesian interpretation is very old. That's essentially what Airy was about. The more modern idea that p-values somehow give significance too easily is related to using a different sort of prior distribution altogether. It may be useful on occasion, but it requires justification. And in any case, it ignores the problem of false negatives. I reject any discussion of this particular problem, which is only in terms of false positives, because a ludicrously easy solution can be given if that's the case. I'm unenthusiastic about automatic Bayes, but I accept that we need to have many ways of looking at data. But there are problems of data analysis we need to take seriously that transcend choice of inferential framework. I'm going to skip that. And these are the other problems: publication bias, hacking, multiplicity in the sense of concentrating on the good news, surrogate endpoints, and naive expectations. So my final conclusions: p-values per se are not the problem. There may be a harmful cultural significance, however this is defined, but I'm sure we could have significant Bayes factors or impressive Bayes factors, or whatever particular adjective we'll use. P-values have a limited use as rough and ready tools using little structure, but you may have more structure and then you should use it, likelihood, Bayes, etc. Point estimates and standard errors are extremely useful for future research. Synthesizers should be provided regularly. We need to make sure that estimates are reported honestly and standard errors calculated appropriately. We should not confuse the evidence from a study with the conclusion that should be drawn. And finally, a thought about laws or hypotheses from George Boole. When the defective data is supplied by a hypothesis, the solution will in general vary with the nature of hypotheses assumed. This was quoted, by the way, by Fisher. In worrying about the hypotheses, let's not overlook the defects of data. And finally, I leave you with this thought. Oh, I'm not going to leave you with this thought. Okay, that's fine. Thank you.